NASA found something strange on Mars. Imagine yourself boarding a spacecraft, destination Mars, knowing the moment you leave, you are never coming back to Earth. Not because of a technical problem, not because the rocket runs out of fuel, because your own body will make it physically impossible. Most people assume this is an engineering challenge: build a faster ship, solve the fuel, come home. But here is what nobody tells you. By the time a Mars astronaut finishes the mission, their skeleton, their heart, and even their brain will have transformed into something that simply cannot survive Earth's gravity anymore. Scientists have a name for this. They call it becoming a Martian body. In this video, I'm going to walk you through exactly what happens system by system to the human body on a Mars mission, and why the return trip is not a choice anymore. Stay with me, because the second point is the one that will genuinely keep you up at night. Here is your expanded version. Here is something that will completely change the way you think about space travel. Right now, when people imagine a mission to Mars, they usually imagine rockets, technology, landing systems, maybe even astronauts planting flags on a red planet. It feels like an engineering challenge, a problem of propulsion, fuel, navigation, and communication. But the real barrier to Mars is not the spaceship. It is the human body. And once you understand what actually happens to a human being over a journey to Mars, you realize something unsettling. We are not just talking about survival in space. We are talking about becoming biologically incompatible with Earth itself. Let's start with the bones. A healthy 30-year-old astronaut leaving Earth for Mars does not stay the same inside their own skeleton. In fact, by the time they return, their bones could resemble those of someone suffering from severe osteoporosis in old age. But not at 70, at 32. This happens because bones are not static structures. They are living tissue. On Earth, gravity constantly puts pressure on the skeleton. Every step you take, every movement you make signals your body. These bones are needed, so the body keeps them strong, constantly rebuilding and reinforcing them. But in space, that signal disappears. In weightlessness, the skeleton no longer feels load. The body interprets this as a message. These structures are no longer necessary, so it begins shutting down bone maintenance. Bone formation slows dramatically, while bone loss continues at full speed. The result is brutal. Astronauts can lose up to 1 to 3% of bone density every single month in microgravity. Over a long-duration mission to Mars, 2 years, maybe more, that adds up to catastrophic loss. In extreme projections, more than half of total bone density can disappear. That means the hip joints, spine, and femur, the very structures responsible for supporting the body under Earth's gravity, become fragile. Not weak in a normal sense, but structurally compromised. And here is the terrifying part. When that astronaut returns to Earth, gravity does not politely reintroduce itself. It hits immediately. The body that adapted to weightlessness suddenly has to carry full gravitational load again. Bones that have been stripped of density may no longer withstand the pressure. Even something as simple as standing up could risk fractures. At that point, the astronaut is not just recovering from a mission. They are fighting to readapt to the planet they were born on. And bones are only the beginning, because at the same time, something else is happening inside the chest. The heart is a muscle, and like all muscles, it responds directly to demand. On Earth, it works constantly against gravity, pumping blood upward, maintaining pressure, keeping circulation stable. In space, that workload changes completely. In microgravity, blood no longer pools naturally in the lower body. Instead, it shifts upward toward the chest and head. The body misinterprets this as an overload of fluid. In response, it reduces total blood volume. Studies on astronauts aboard the International Space Station show that over time, the heart itself begins to shrink. It can lose up to 20% of its mass during extended missions. This is not damage in the traditional sense. It is adaptation. The heart becomes more efficient for a low-gravity environment. It no longer needs to work as hard, so it becomes smaller, weaker, and optimized for conditions that exist only in orbit or on Mars. But here is where the problem becomes dangerous, because when that astronaut returns to Earth, gravity is no longer gentle. It demands force. The heart now has to push blood upward against full gravitational load again. But it is no longer the same organ. Astronauts returning from just 6 months in space often experience dizziness or fainting when they try to stand. Their cardiovascular system struggles to cope with Earth's demands. Now imagine that effect multiplied over 2 or 3 years on a Mars mission. The heart does not just weaken, it becomes adapted to a different world entirely. A Martian heart cannot immediately function in Earth gravity. And then there is the most silent threat of all: radiation. On Earth, we are protected by 2 invisible shields, the atmosphere and the magnetic field. Together, they block nearly all high-energy cosmic radiation from reaching the surface. In deep space, those protections disappear. A spacecraft traveling to Mars exposes its crew to continuous cosmic radiation. Over the full duration of a mission, astronauts may absorb radiation equivalent to thousands of chest X-rays. But the danger is not just cancer risk, although that alone increases significantly. Studies suggest that long-term exposure can lead to measurable cognitive changes, slower processing speed, reduced memory performance, and impaired decision-making ability. These are not immediate symptoms. They develop gradually, silently, over time. By the end of a Mars mission, an astronaut may not notice these changes clearly, but the damage is already there. At the same time, radiation affects the immune system and bone marrow, weakening the body's ability to repair itself. It also accelerates cardiovascular aging, effectively pushing biological systems years or even decades forward in deterioration. So while the bones weaken and the heart shrinks, the brain is also being subtly altered, not destroyed, but changed. And what makes this even more complex is that a Mars mission is not a single environment. It is 3 completely different gravitational realities. First, there is complete weightlessness during the journey to Mars, about 6 to 9 months of microgravity where the body begins rapid adaptation. Then comes Mars itself, with only 38% of Earth's gravity. That is not enough to restore normal bone density or fully maintain cardiovascular strength. It slows degradation, but does not stop it. The body is still unlearning Earth. Then comes the return journey, another extended period of weightlessness. Each transition forces the body to readjust. Each change is a shock, and instead of recovering between phases, the body is constantly adapting to new physics. By the time the mission ends, the human system has not just weakened, it has reorganized itself. Bones adapted to low load, a heart adapted to low pressure, a brain exposed to cumulative radiation damage. And here is the most important conclusion scientists are slowly reaching. The barrier to Mars is not engineering. We already know how to build rockets capable of reaching it. The barrier is biology. Because even if we can send humans to Mars, we do not yet know how to bring them back as functional Earth inhabitants. That is the paradox. The mission does not just take humans to another planet. It slowly converts them into beings that belong somewhere else. And when they return, they may no longer fully belong here either. So the real question is no longer, can we reach Mars? The real question is, can the human body survive being rewritten by space itself? And right now, the honest answer is still unknown. The first humans to reach Mars will not be explorers who come home with stories. They will be permanent settlers not by choice, but by the physics of what a human body becomes. Which means the real question for humanity is not how do we get to Mars? It is, who is willing to go and never come back? If this changed how you see the Mars mission, share it with someone who still thinks this is just a rocket problem. And watch this next, it covers what a one-way Mars colony would actually look like.